My name is Jonathan Charlton. I go by JR. And I am going to show you a machine that I've written that answers yes and no questions. In fact, it answers any yes or no question. And it does so providing an intelligent response. So I'm going to go ahead and demonstrate that. What I'm going to do is I'm going to type my function. So the name of my program is called moo. And moo is a program which, when I press enter, will give me a true or false prediction. So we're going to say true is yes and false is no, or just true is true and false is false, or true can be represented by 1 and false can be represented by 0. And moreover, we can have true represent red, false represents black. And you can go vice versa on these, as just as long as you're consistent with your assignments. So we're going to go ahead and ask move for a prediction, and it's not a prediction really, it's a guess. And this particular machine guesses. It doesn't use any data to make this prediction. As you'll see, it's just going to provide a guess. And then what's going to happen is when it provides that guess, we're going to query the event, get the outcome, and then tell moo whether or not it got it correct. If it got it correct, if it got it correct, or we'll tell moo the outcome. So for instance, if we flip a coin and we call heads true and tails false, and it comes up, and let's say moo guesses that the outcome of a coin toss will be true. It's guessing that the outcome will be heads. If it guesses that the outcome is heads and it is heads, we'll enter 1 into the computer to let it know that it was heads. If it comes up tails, we'll enter 0 to let it know that it was 0 or tails. And that will inform the computer whether or not its prediction or guess was correct. And then it will ask if we want to do that again, and we will give it a 1 for yes or a 0 for no. Let's end this. And if we say yes, it'll give us another prediction. So what we're going to show here with this machine is it will answer any yes no question and become more intelligent on the event. And we're not just going to do that on coin tosses, we'll do that on other things. So first, coin tosses. Here we go. We're going to press enter, and it says the NTM guesses the outcome will be true. What that reads is the non-deterministic Turing machine guesses the outcome will be heads in our particular event. And it's saying please enter 1 if the outcome is true or 0 if the outcome is false. So enter 1 if the outcome is heads and 0 if the outcome is tails. And it is predicting that the outcome will be heads. So we're going to go ahead and flip, and it comes up heads. So the computer was right, and we tell it that it was heads by putting in a 1. That comes up, and we have a new set of graphs here on the right that are generated to tell us how our computer is doing, which I'll explain as we get more data points. But what we have here on the left is these first pieces of information here are just the console, and this is the R programming language, telling me, hey, essentially, hey, you've got some graphs here, but you only got one data point. Are you sure you want to graph this way? This will go away after every other prediction, or guess. But anyway, the guess, what it's now saying is the NTM has been correct 1 time out of 1 guesses for an accuracy of 100%. And so what you see here is the NTM guessed heads. It came up heads. We told it that it was heads, and so it's not marked that, said that, and it's asking us if we want to make another guess. We enter 1 to say yes. And so it's now guessing that the outcome of the next coin toss will be false or tails. So we will flip again. And it comes up tails. So we enter in 1 if the outcome were heads and 0 if the outcome were tails. The outcome is tails, so we're entering in 0. And that will tell the computer that it again got the answer right, or the prediction right. And what you see here on the graph is this blue line up here at the top represents the accuracy, the cumulative accuracy over 2 guesses. 1, 2. I know it's got these decimal points, but that's just a relic of the graphing. In any case, or the graphing parameters. But in any case, if this line, if the cumulative accuracy were to be less than 50%, so when this line drops to 50% or lower, it will turn red. And down here, you have another set of lines, and all this is saying is, on each choice, how did I do? The blue line is representing the machine and will always represent the machine on all graphs until the machine's performance cumulative accuracy drops below the 50% line here, in which case it will switch red. So these down here will switch positions if ever or whenever the machine drops below 50% accuracy, cumulative accuracy. But right now it's at 100%. So what it's saying is, my first guess I got correct, I gave it a 1. My second guess I got correct, it's got a 1. And the red line represents the opposite, and that makes it easier to see patterns, as you will see. Anyway, the NTM has been correct. Over here we see the NTM has been correct 2 times out of 2 guesses for an accuracy of 100%. We want to continue, and we press 1. It guesses that the next outcome of a coin toss will be tails, so we will flip the coin again, and it comes up heads. So what we do is we tell the computer, as it says, please enter 1 if the outcome is true, or heads, 0 if the outcome is false, or tails. The outcome here was heads, so we enter in a 1. Its prediction was tails, so what we should see is 2 out of 3 on the accuracy, or 66.6 repeated percent, which is exactly what we see. And you see the graphs adjust. So on the third guess here, so guess 1 I was correct, or the algorithm was correct. Guess 2, the algorithm was correct. Guess 3, it was incorrect. And my accuracy is at 66.6%. And we want to continue, so we will press 1 to continue. And it's guessing that the next outcome will be heads. So we flip again, and the outcome is heads. So we put 1 down for true, or heads, and so we should be at 75% accuracy. And you see that reflected there, and you see the correct choice reflected here. You see this third graph. This third graph simply takes all the data points and bends them into quartiles. You could have deciles as well. It's just a simple parameter change, but on this particular demonstration, it's the quartiles. So as you can see, we get the first guess correct, the second guess correct, the third guess was incorrect, the fourth guess was correct. We can continue if we like. We press 1 here to continue. It guesses the next outcome will be heads. We flip again, and the outcome is heads. So we press 1 to let the computer know that. We'll go to 80%, and you will see that reflected here in the data. The quartiles, of course, change, and what's happening is one of the data points is being binned in here. So as the data points bin into each of the quartiles, they start affecting the overall percentage of correct answers that are reflected here. Any case, we've shown how it works on a coin toss, and really to demonstrate the full power of this, we just keep doing coin tosses as long as you like. And what it's really testing is whether or not the generator itself is random, as we might define it at 50%, or not. But really, we might think of it as whether or not the statistical pattern itself can be learned, and that is what this machine is doing. In any case, I will press 0 to end this query, and what we will now do is go over to a roulette wheel. And so we have a roulette wheel right here, and just for fairness sake, we will take that off and do this again to start over. showing no gimmicks. And here we are. So we have red, we have black, and what we're going to do is predict whether or not this roulette wheel from this computer program on the internet is going to land on red or black. We could also do even or odd, you know, the first 18, the other half 18, and these thirds, there's a way of doing that, but that's for a different video. It was really important is to show you and to show how these can be turned into yes/no questions. But these are very easy, straightforward yes/no questions to see, so we'll demonstrate those. In any case, we're going to predict whether or not this roulette wheel will land red or black, and we're going to call, for argument's sake, red true and black false. You could think of it as heads and tails. It doesn't matter as long as you're consistent. So anyway, we're going to invoke our function here, and it will give us a prediction. It says that the outcome will be red, or true as we're calling it here. So we will put money on that, and we will spin.
No more bets, please.
Let's turn off the volume.
31. Black. Odds.
So it comes.
Place your bets, please.
Turn off the sound. So it came up black, which is false. So we'll put in the 0, which would tell the computer it had gotten its first guess wrong. You'll see that here. There's the thing about the graphs, but the NTM has been correct 0 times out of 1 guesses for an accuracy of 0%. We want to continue. So we press 1, and it gives us that the next outcome will be black. We go on black, and we spin again. It lands black, so we enter in 0 to let it know which way it came out and that its prediction was correct, and we are now at 50%, and as you can see, the line is at 50% or below, so it's red. Here, the machine is represented by the red line until this line here goes above the green line, which would turn everything blue. So we'll put in 1 saying we want to continue, and it's guessing the next outcome will be red. So we will spin on red and see if that is how it comes out, and then inform the computer how it has done. So it comes out red, and we tell it got red, that it was true or red, so we enter in 1, press enter. The graph updates. As you can see, the lines have now then turned blue that represent the outcome of the machine, and its antithesis is here in red. We want to continue. We press 1, and it says that the next outcome will be red, so we will spin to see if that is true or if that actually occurs. And it comes up black. So in this instance, the machine was wrong. We tell it that it was black by putting in the 0. We press enter, and you see it back down to 50%. Thus, the line has now turned red again. We tell it we want to continue. It says the next outcome will be red. We click and bet and spin again. The outcome is red. We press 1 to let it know that it's red. And so we have an outcome of 60%. And we could tell it we want to continue again. So let's say, because I think we only did 5 data points in the last one, we'll do another one just to show. So we want to continue. It's guessing that it'll be red again. Why not? And if it comes up green, it's kind of like a do-over. It'd be like flipping a coin and it landing on its edge. So it comes up red, so it got it correct. And we tell it it was red by putting in 1, pressing enter, and you see the graph go to 66% here. 2/3 of our guesses are correct. And so it doesn't really just rely on coin tosses or roulette, random games of chance. Essentially, this is a machine that if you ask it any question for that matter, I could just say, are the number of fingers I'm holding up behind my back greater than two, right? And I could keep repeating to see if the machine could learn if there was some prior behavior or prescription, let's say, for how I am choosing, maybe perhaps unbeknownst to my conscious, but my subconscious, the way it chooses how many fingers I am holding up to try and trick it or to try and test it. So that's what this machine does. And as you can see, it does so without giving it any data whatsoever. It does not matter what data you give it, how far away you are, what you're observing, as long as it is a yes, no type of question, this machine will answer it and it will get smarter. And so I would ask for people to consider when we think about what kind of machines do this, right? What kind of machines answer yes no questions, no matter what yes no question there is, and keep asking, hey, what's the next question? What's next, right? That is something to consider, but that is what this machine will do, and you can keep giving it more and more questions, and it will keep getting smarter and smarter. Um, so until it mimics whatever prior statistical pattern is exhibited by the choices or the outcomes in a particular event that one is observing, and that has certain implications that I think ought to be discussed. But this is my yes/no answering machine called Moo that I wrote, and it is. So I hope you will consider what that means. If you know what that means, do you know what that means? And what I really would like to request is, to me, this is, um, this is a pretty interesting machine that I've created. It's pretty small, but I'd like to request, to some extent, some help with asserting that when we talk about problems like P versus NP, and people stating that with a lot of, I don't know, what would the whatever attitude it is, the common attitude is that if you are not in the P does not equal NP camp, you are insane. And we have lots of people out there with good reputations that don't agree, and the very fact that P doesn't equal MP is an argument that is based entirely on speculation as opposed to any real proof whatsoever. Should give pause for notice. Based on the machine that I have, it would seem obvious that I am in the P equals MP camp, and that I would assert that my machine is a proof that P equals MP. The reason I am making that argument, that very specific argument, is because the person who might be thought of as to really formalize or to conceptualize or even incept the idea itself is Gödel, Kurt Gödel, who wrote essentially, if you have a machine that can answer yes no questions, then, and it doesn't care what question, then I mean, you've essentially solved P equals MP. And we're not talking about just, hey, a computer that does it just on a coin toss and has absolutely no demonstration of intelligence whatsoever. It would have to defeat a Turing test, and this, we can show how it defeats a Turing test, but ultimately the question is, does my machine do this statement by Kurt Gödel, right? And to zoom right into that, it is right here. And that question was posed by Gödel in 1956. It's right here in a quote. The P equals MP question, and Gödel's lost letter, which is to John von Neumann at Princeton in 1956, in March of 1956. The essentially, the way I see it is, Gödel was dealing with some relics from, I guess, Riemann and Euler, I think, about parallel lines and getting to decidability, and he was dealing with, he's a Platonist, or I believe that's how they refer to it, and he was dealing with some mathematical finitist view, um, and I might argue in favor of finitism given what I've found. But I wouldn't consider myself an expert in that argument, although I definitely think it's something to talk to. But in any case, I think Gödel was sitting there writing about undecidability or incompleteness and came up with something profound on incompleteness in his theorem. And Turing and Church later wrote via the halting problem, expanding upon that, the limitations of computers given incompleteness, and the limitations of computers and what they can solve. And then I think later in life, both of the men kind of reflected on that at a much deeper level. So Turing, I think, in 1950, probably, I think that was when he wrote the Imitation Game article on computing machinery. I think he kind of tickled the idea that, well, wait a second here. What if we had a machine that could trick a human? If that could happen, then if we had the ability to write how we're doing it, I mean, necessarily that would be kind of like an automated problem solver, right? Because we're the ones who solve problems. If we could write something that does what we're doing, that in and of itself would kind of show that we know how we're doing what we're doing, and that it can be done, it can be programmed. And I think Gödel then expounded upon this himself, his own incompleteness, by postulating this very question and saying if we could create such a machine. And then later in the 70s, Stephen Cook and I think Leonov, I can't remember his first name. I think they independently came up with the understanding or formalization of all these complex problems and the way to solve them, as indicated by Gödel, if there were a way to solve them, as the P versus MP question. And I do believe that, and all these problems were shown to be the same problem by Gary and Johnson, and I think David Johnson in the 1970s, maybe 1976 or 74, I can't recall. In any case, I have a machine that does what Gödel said, as best I can observe. It takes no data in, and it can answer any yes/no question. So to me, I have a solution to P versus MP in the affirmative that P equals MP. And what I don't need is people saying you don't know mathematics or you don't have a background. I don't have your traditional background in mathematics. I have a MS in finance and an MBA, but I have quite an extensive amount of experience in the field of mathematics across military operations research, designing tracking algorithms, all sorts of different, stock market valuation or trend prediction algorithms, mostly designing my own forms of autoregressiveness. But, the language that I use to kind of, I know certain aspects of mathematical language that suit my particular areas of expertise. And admittedly, I'm applied in that sense. But in terms of my ability to translate a solution for P versus MP, it comes down strictly to computer code. So I can answer why P equals MP in the form of functional code, which I have. And if I'm correct, then the means by which one would communicate that is very difficult, because in my mind, the entirety of the P versus MP question is, and the way that it might be received, a response might be received by academia or by any entity that could recognize such a solution, is somewhat biased towards the assumption that P does not equal MP, which in their response is wholly acceptable, or their method of reception of such a solution is wholly acceptable if P were not equal to MP. It'd be totally safe to hand out $1 million award for something like that. But if the converse is true and P actually equals MP, as I'm asserting, then that is not a very responsible way of soliciting proofs of P equals MP. And I do think that it requires a much more considerate of the author type of response, as well as the receiver, and what kind of position that puts them in from a geopolitical standpoint. And despite the fact that I may have a background that one might think, hey, that's not somebody to solve P versus MP. I just have to say to you, actually, my background is perfect for having done so. My career in military operations research, introduced me to MP completeness. And over the many years of having applied that, whether or not I had the degrees at the time, that I did have the clearances to be asked to do that work, my brain has been used to think through that problem consistently on a day-by-day basis for the past 20 years. And so, like any student of mathematics, I seek out, after understanding the philosophical question and where the math I'm seeking emerges from, I definitely become interested in the utility of that mathematics and develop my own system autodidactically, or if other people are willing to teach me. I develop my own system for trying to solve that problem. And so I would assert that I have, and if I have, which I would really request, if you are a critic of what I have, then please tell me how a machine that does exactly what Gödel has said, what Halting has said, would be amazing, or sorry, what Turing has said would be amazing if it existed, and would be the solution to what we think of as P versus MP, and moreover, the Entscheidungsproblem. Please tell me why that's not the case, why it's not what you just saw in front of your eyes. And if you do kind of want to lend weight to that being a potentiality, then I would ask, what scenario do you see where it doesn't result in, some sort of apocalyptic winter, and how would you release that? The best way that I can think of is seeking political asylum in a non-superpower country as a means to making all the other superpowers, I suppose, not aggressive with one another. Um, and at the same time providing sanctuary for the person who discovered it and the entity that received it. So what kind of non-superpower is protected from all the superpowers? And I would think it would be a geolocation issue, as far as even though information and the implication of P equaling MP is well beyond distance itself, um, for the lay person, they may not understand that, and so the appearance of distance for the lay person who may be in a decision making role or not, um, is important to keep up. And at the same time, that location, I would think, need to be a nation state that had certain treaties that protected it and kept it in perhaps not a non-neutral circumstance, but at least in a one that has credibility across all sides, as an independent authority, worthy of um, maintaining the solution. Moreover, in such a nation that had that, the obvious position to me would be that it would seek to, upon having solidified its position with the solution, would be to not necessarily sue, but negotiate for the denuclearization of the rest of the world, in exchange for the solution itself. And I think any nation with a mathematician of base intelligence that understood the P versus MP problem would recognize that if it were true that a certain nation state, let's say non-nuclear superpower, um, or non-nuclear power, or non-superpower, or whatnot, just not superpower, were to have such a solution, and it were impractical to either A, annihilate it, or B, take it, then it would be absolutely within the realm of desirability to negotiate to get the solution, anything that you want, because P versus MP is more powerful than any and all nuclear weapons put together, as well as all nuclear energy. It really gets to the heart of how that energy is created, and then you can, or at least how to mimic it or clone it, or there a lot of the language I think breaks down in terms of describing the potentialities with the solution. Of course, many people watching this might be glazed over, or they may be interested if they actually really understand what they had just witnessed. Um, Either way, um, this is what I know to do, and I'm going to continue doing it. I put it up on certain platforms because they are the platforms to which I have access to people who might understand what this problem is and what this machine is doing. Um, so yes, if you have any thoughts, I have my first inclinations of where and what to do with this, but really, what would you do if you had a P equals MP machine? Um, I would ask for help or try and get to safety.